All right, welcome to another great video. So in this particular video, we have this problem. Right, this is a Newton's second law question, and then in this particular question, we are given, as you can see, there's a trolley, there's a ramp, and the ramp is at an incline of 4.76 degrees. Okay, so when we read the statement, they're telling us that this is a recommended angle for ramps by the national building regulations. Okay, and also that the ramp must be 6 meters in length. So this means this guy, this whole thing, actually let me use it, means that this whole thing, this length will be 6 meters, right? And then the angle of the ramp is given to us. The combined mass of the trolley and its contents is 80 kilograms. So this means that whoever was doing shopping here, their combined items plus the mass of the trolley amounts to 80 kilograms. It's quite a heavy trolley. 80 kilograms is like almost the average mass of an average adult. So now the coefficient of static friction between the wheels of the trolley and the ramp is 0.1. Okay, we are told that mu is 0.1, 0.1, which drops to 0.09 once the trolley is moving. So notice what they did here. They're saying this thing drops to 0.09 once the trolley is moving. We know that the only kind of friction that we experience once an object is in motion is the kinetic friction. So what that tells us, or what this hints at, is it means that the coefficient of kinetic friction is also given, and we can assume that it's 0.09. All right, so we have this piece of information, and then we are also told the length. I'm not sure what to call our length. Let's call it delta x. Our delta x is 6 meters. Right, so let's leave it here. We have the information now. So let us annotate our diagram. Remember, that's always our first step. We just take out all the forces that we know are there. So we can take out normal force. Normal force is there because this trolley is in contact with the surface. Let me use red so that it just screams out of this page. So we have that. We can take out normal force here. It has to be perpendicular to the surface. Right, so let's just do it like this. Yes. We have normal force. And then, remember, we have weight, which acts straight down. Okay, my weight looks skewed, but it must act straight down. That is my weight. And then we will have friction resisting here, resisting the tendency of this trolley to move downward, or resisting the trolley's motion downwards. So if it's still not moving, we will experience static friction. If it starts moving, we will experience kinetic friction. So right now, I won't mention whether it's K or S because I don't know whether it's moving or not, but let's just say static friction. Yeah, it's fine. So these are the forces that we have for this particular trolley while it moves down the ramp, or while it tends to move down the ramp. Right, so let's go to our questions now. 3.1, define the term static friction. We know that static friction, by definition, it is the force that opposes the tendency. The keyword there is tendency. It opposes the tendency of motion of an object that is not moving. Or in short, it opposes the tendency of motion of a stationary object. Right, those two are the keywords. The keyword is tendency and stationary. That's where your 2 marks comes from. So it opposes the tendency of motion of a stationary object. Tendency of motion of a stationary object. So it only acts on objects that are not moving but they want to move. Right. So that's the static friction. Now we're asked to draw a label diagram showing all the forces acting on this trolley. Now if you check the trolley, and we've already annotated it, so we know all the forces that are acting on it. So you can just take that diagram that we did there, but now turn it into a free body diagram. Draw a labeled diagram. This is very weird. They didn't say free body, but I prefer a free body diagram. So let's use a free body diagram. I'm guessing you could have drawn a force diagram. It was still gonna be fine because they're not specific whether they want a free body or a force diagram. So I prefer a free body diagram because I know that 99.99% of the time that is what's mostly required. The other 0.01% is this instance right here where it's not specified. So now we have this normal force, like we said, and then we will have weight acting straight down, and then we had friction going that way. Let's call it Fs. Okay, I'll call it Fs for now. So this is our free body diagram. Okay, so that's all we had to, oh, I forgot to annotate this one. W or Fg. Some people prefer Fg, which means force of gravity. I prefer W. And then here it's either N or Fn. Depends which one you use at your school or which one your teacher prefers. Or which one you prefer actually. So you use that one. There's no punishment. So now that's it. We have our 3 forces. That's why this thing is 3 marks. If you take note of this, it's 3 marks. If you check here. So they will mark your 3 forces there. Now let's go to 3.3.1. While the trolley is at the top of the ramp, okay, calculate the normal force. All right. So if you remember, I always say when you find the normal force, what you are essentially doing is you are taking a sum of all forces acting perpendicular to that object and then equating that to 0. So in grade 11 and 12 high school physics, right, we know that most of the time we will focus on one direction or unidirectional motion. So motion in one axis, 1D motion. Okay, so we know that since this trolley is moving down like this, we can assume that it's not moving up or down. So F net is equals to 0 in the perpendicular direction. So that's where actually the normal force is calculated. So what I mean by that is, if we take our free body diagram there, and then obviously we will have weight components. We will have, let's see, we'll have a weight component here, which will be our weight y, or weight perpendicular. It's in line with our normal force. And then we will have an x component, or a parallel component of w. I don't know why I said y. I meant w. x. Let's call this wx because it acts along the x-axis or in the parallel axis. So, parallel to the x-axis. So now, these are the components that we have. And remember, we put our angle here between the y, or between the perpendicular component and the actual vector itself. Right. So that would be 4.76 in this case. So if you check in the perpendicular direction, if we take a sum of our forces there and we say F net is equals to naught, right? And we take the direction of n as positive, which makes our job simple. We'll have n minus weight perpendicular is equals to naught. And then if we make n the subject, we know that n should be weight perpendicular, or the y component of weight. Now what we do after this, we want to know what is weight perpendicular, or what is wy. If 4.76 is here, then wy should be w cos theta, like this. So we know our theta, we can find our w. Right, so we can say n is equals to mg cos 4.76 degrees. Was it 4.76? Yes. So you could have just substituted everything here. The mass of the trolley is 80, and we have 9.8 being the gravitational constant, cos 4.76 degrees. And this right here gives us 80 times 9.8 times cos 4.76. Make sure your calculator is in degrees and not radians. So you should see D there and not R. If you see R, you better pray you don't see that R after an exam, because then there's nothing you can do to change. But if you see it during the exam, you can always change. So now, that's all. This is our normal force. This is the magnitude of the normal force. Right, so it's positive and it's going up, or in the perpendicular direction to our surface. Right, so now we have 3.3.2. For 3.3.2, we are required to calculate the maximum force of static friction. We know that Fs max is mu s times n all the time. Right, were we given mu s? Yes, we were given, which is 0.1. So we'll have 0.1 times 781.30. This should be 70. Okay, let me just do it. Should be 78 point something, because that's 10%. 781.30 times 0.1 is 78.13. All right, newtons. Simple 3 marks. Is it 3 or 2? Oh, it's 2 marks. So that's it. That's all you had to do for this one. Now we have 3.3.3. 3.3.3 says now we have to explain with the aid of a calculation whether the trolley will start to roll down the ramp, or whether the trolley will start to roll down the ramp on its own or not. So here the thought process is this. They wanted to check if you understand what happens before the trolley, for the trolley to actually roll down, what happens. So here's the story, right? If you remember, we said for any object to start moving, any force that we apply on the object, or any force that is applied on the object, must overcome the maximum static friction. Only then will the object be able to move. So now our question becomes, if it must overcome the maximum static friction, then what force is it that will likely drive this thing to move? Because there's no applied force here. So we want to check for forces that are in this direction, because this thing is likely to move there, right? So when we come to our free body diagram, we see that we have the parallel component of weight. That's the only force that will move this trolley on its own. So this trolley will move as a result of its weight, its parallel component to be precise. So now that's what we want. We want to see if Wx will be greater than Fs max. If Wx is greater than Fx max, this thing will move. While if Wx is less than Fs max, this thing will not move, because it means the forces will be balanced and this trolley will remain wherever it is. Let's check. So let's find Fx max. Let's find Wx, because we already have Fx max. Wx is equals to W sine theta, which is mg. Let me just write it here. Okay, you don't have to have 3 equal signs. Which is 80 times 9.8 times sine 4.76 degrees. Now what do we get? 80 times 9.8 times sine. This is 65.06 newtons. Now let's go and compare it with Fs max. So when we are checking Fs max, we find that Wx is less than Fs max. Right. If Wx is less than Fs max, which is the maximum static friction, it means this thing won't move, because it won't be able to overcome the maximum static friction of the trolley. Therefore, the trolley will not move. So that's all you had to do for this particular problem. So if you had this one in your exam, you were very lucky. It was quite a straightforward problem for you. And then yes, so that's all you had to do for this one. And then yeah, thank you. Catch you on our next video.